In this section, we will cover related rates. The idea behind this topic is, if you have an equation that connects variables, how do those variables change over time? And when you find those rates, how do they compare to each other? To get the ball rolling on this, I have a couple of equations. I'd like to first differentiate them with respect to the variables that appear within the equation themselves. And this is basically something we've already done before, but I'd like to just take a second look at this process. Like here, for a is equal to pi r squared, this is the formula for the area of a circle if you know the radius. I'm going to take the derivative of both sides with respect to r. And this is a really simple thing to do. Over here, you bring down the 2, copy down the pi and the r, subtract 1 from the exponent, and you're done. And your answer is 2 pi r. If I was being very careful, it would look like this. Bring down the 2, copy down the pi, you would subtract 1 from the exponent of r, and then by the chain rule, you'd multiply by the derivative of this thing with respect to r, which is dr dr. But of course, we never write that because that derivative is always equal to 1, and our answer is the derivative of the area with respect to r is simply 2 pi r, and that's it. What about taking the derivative of this equation with respect to x? So this would be implicit differentiation. Let's try it out. So let's see. For x squared, if you take the derivative of x, you get 2 times x to the first. If you were being very careful by the chain rule, you'd multiply by the derivative of x with respect to x. We never wrote this because it's equal to 1, but I'll put it there for now. You would then add on. All right, now you take the derivative of y squared with respect to x. You get 2. You get y. But then you get y prime, which is dy dx. And on the other side, the derivative of 9 is 0. Again, we wouldn't express our answer this way just because dx dx, this thing here, is equal to 1. But the answer is 2x plus 2y dy dx is 0. You could then solve for dy dx and you'd be done. Okay, but what about if we want to differentiate with respect to a variable that does not appear within the equation, in this case t, which will represent time? How would you go about doing that? Let's start over. I'll look at a is equal to pi r squared. And this time I'm going to take the derivative of both sides with respect to t. On the left, that's dA dt. So you took the derivative of area with respect to time. On the right, you're taking the derivative of this thing, which means you bring down the 2, copy down the pi and the r, and you subtract 1 from the exponent, 2 pi r. But you have to multiply by the derivative of this thing, this time not with respect to r, but with respect to t. And this is the answer. The difference here is, when we took the derivative before, we never actually had to include this because it was always equal to 1. If you now introduce another variable, well, now you do have to include it because this thing might not actually be equal to 1. It doesn't cancel. Let's try this down here. Again, we're going to start over and we're going to look at x squared plus y squared is equal to 9. And again, I'm going to take the derivative of both sides with respect to time. Starting with x squared, you bring down the 2, copy down the x, and subtract 1 from the exponent. But then you have to multiply by the derivative of x with respect to time. Over here, we didn't really need to write this because, again, it was equal to 1. Over here, this thing does not cancel, but it must be present within the equation. Okay, moving on. What about the derivative of y squared? That is 2y, and now I have to multiply by the derivative of y with respect to t. On the other side of my equation, the derivative of 9 is a constant is equal to 0, and this is the answer here. So it looks a little bit different in that we're now including these other terms that appear after you take the derivative with respect to time, but the concept behind it is really the same. Let's try this in an example. Let's go back to the area of a circle, which is a is equal to pi r squared. This isn't a calculus question, but it's a question you can answer using this formula. If a circle has a radius of 4 feet, how much area does it occupy in square feet? The way it works is you take your formula. In place of r, you put 4. You could actually even include the units of feet if you'd like to. And all you have to do is multiply this out. 4 squared is 16, so this is pi times 16. You actually also square the units too, and you get square feet, which is good. Area should be square feet. And, well, we probably would reorganize this as 16 pi, and that's square feet. So if you know a radius and its distance, and you put it into this formula, it'll tell you the amount of area that this circle will occupy. Now let's ask a calculus-based question. So let's say you have a circle. I'll draw a circle. And it has an area and also a radius, which I'll draw a radius in here, r. If you can think about the circle and its radius is increasing, that means the area is increasing too. What are the rates at which the area and the radius are increasing? The rate at which the radius increases we would call dr dt. The rate at which the area increases is dA dt. If you know one of these, you should be able to figure out the other. So like, for example, if you knew that the radius was increasing at some fixed amount, could you determine how fast the area is increasing too? And the answer to this question, of course, is yes. So let's check this out here. Suppose the rate at which the radius of a circle is increasing is 2 feet per second. So we're told this thing, it's 2 feet per second. Can we determine how fast the area of the circle is increasing when the radius reaches 4 feet? The process would go like this. You have to choose an equation that connects the two variables that you're interested in this case, the area of a circle, and also its radius. If you want to answer a question about how are these variables changing, you have to take the derivative of both sides of the equation. But more specifically, you have to take the derivative with respect to time. And this is what we did on the previous slide. On the left, the derivative of area with respect to time is dA dt. If we do the same thing on the right, you get 2 pi r, and by the chain rule, you get dr dt. And look what we have. We have a brand new equation, and equality is true because we did the same thing to both sides. On one side, we actually have something that tells us how fast the area is changing, and on the other side, we have something that tells us how fast the radius is changing. Well, we're actually given dr dt. It's 2 feet per second, so I'll put that over here. This is given information. And what else do we know? If we want to know this, how fast the area is changing, not only do you have to know how fast the radius is changing, but you have to know how long the radius is as well. And we're told, well, what's this when r is equal to 4 feet? So I'll say r is equal to 4 feet. I'm going to take this information, put it into this side of the equation, and it will tell me the rate at which the area is changing. Let's check it out. dA dt is equal to 2 pi. The radius is 4. I'll actually include the units of feet. That's being multiplied by dr dt, which we're told is 2 feet per second. When you multiply this all together, we get 2 times 4, which is 8, times 2, which is 16. And if I multiply that to the pi, I get 16 pi. And the units are feet times feet, which is square feet, divided by seconds. So at this exact moment, if you know how the radius is changing and you choose a particular radius, you can actually figure out how fast the area is changing at that moment. And it so happens that it's also 16 pi. The important difference here is this thing is the amount of space that it occupies, but this is how fast the area is actually changing at that exact moment. This is very powerful. If you have an equation and it connects variables, not only do you know how the two variables relate to each other, you can determine how their rates of change connect to each other as well. All right, let's try this idea again. Here in example 1, suppose a spherical balloon is being filled with air. So we have a sphere and it's increasing in size. If the radius of the sphere is increasing at a rate of 0.5 centimeter every second, can we figure out how fast the volume is changing once the radius reaches 12 centimeters? So I'm just going to draw a picture here to help me visualize what's going on here. So we have this sphere, and here's the radius of the sphere, and this thing is increasing in size. Is there an equation that connects the volume and the radius? And the answer is yeah. Volume is equal to 4 2/3 pi r cubed. So at any moment, if you know the radius, you can determine how much space, how much volume this sphere occupies. Okay, but again, it goes on to say the radius of the sphere is increasing at this rate. What is that? That is dr dt. We're actually told it's equal to 0.5, and the units are centimeters per second. And we're also told that, well, if this is the rate at which the radius is increasing, I should be able to figure out dv dt. Can I figure out this number here when the radius reaches 12 centimeters? The strategy is going to be set up your equation and then take the derivative of both sides with respect to time. So here we go. This is my equation, and I'm differentiating both sides with respect to t. On the left, we get dv dt. On the right, I'm going to bring down the 3. It'll cancel with this 3 to give me just 4. I'll also have pi, and I'll have r squared because we subtract 1 from the exponent, 3 going to a 2. What else do we have to multiply by? Well, we're taking the derivative of this thing with respect to t, so by the chain rule, you get dr dt. And if you look at the equation we want to know how fast the volume is changing. And we're told this value here, we're told it's equal to 0.5. And we're also given a value of r as well. We can enter all that information into this equation, and it should allow us to solve for dv dt. This time, I won't put the units in here, just because I have an idea of what the units should be in the final answer. Let's try it out. Okay, so dv dt is equal to 4 pi. The radius is 12 centimeters, and we're squaring that, and we're multiplying that by dr dt, which is 0.5. I'm simply going to type this all into a calculator and multiply it together, see what we get. So we have 12 squared times 4 times 0.5. That's 288. And then we have pi. This is an exact answer. What should the units be? Well, volume, if our distance is centimeters, should be cubic centimeters. So cubic centimeters. The unit of time was seconds. So here we get cubic centimeters per second. If you want an approximation for that, 288 times pi is about 904.8. So roughly this many cubic centimeters a second is how fast the volume is changing at this given moment. So again, the idea being, if you have an equation that connects your variables, you can differentiate it. Now you're connecting the rates at which those variables are changing with respect to each other. I'd like to make an important note before moving on. If you have a variable that is increasing, so the variable is increasing, that means its derivative is positive. So here, for example, we're told that the rate at which the radius was increasing was positive 0.5 centimeters per second. So here, positive value. And here we have the volume, it was increasing as well, and this is a positive number. If a variable is decreasing, that means the rate must be negative. Let's actually look at some more sophisticated examples and come up with a strategy to figure out how to solve these types of problems. The strategies I'm going to use are draw a picture, label in some variables, set up an equation, and then that's when the calculus portion is going to start, where we take a derivative and try to solve the equation that we have. Let's read this problem. A ladder that's 10 feet long is resting against a vertical wall. The bottom of the ladder slides away from the wall at a rate of 4 feet per second. How fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet away from the wall? That's a very wordy problem. To decrease the mental load of everything that's happening, I'm going to try to put all these ideas into a picture, which I'll draw over here. I'll try to keep it simple, but this is my wall, this is the floor, and we're told we have this ladder, which I'll draw like this, and that ladder is 10 feet long, and it starts out that it's just resting against the wall perfectly like this. Now, at some point, we're told, okay, well, this part of the letter starts to slide in this direction away from the wall, meaning this part's going to slide down the wall. If you know how fast this part is moving, can we figure out how fast this part is moving? Maybe they're the same, maybe they're different. I don't know. I'd like to try to analyze this. To do so, we're going to need an equation. And if we need an equation, I have to set up some variables. And what I'm noticing here is we have a right triangle. And I know this side is always 10. I'm going to call this side x. That's the distance from here to this spot on the ladder. So here, this side I'm going to label as x. And then from here to here, I'm going to label this distance as y. Is there an equation that you can think of that will connect x, y, and 10? And here, you can do so by using the Pythagorean theorem. X squared plus y squared is equal to 10 squared, or 100. So that's step one. Draw a picture. Step two, label some variables. Here's our equation. I'm going to want to differentiate this thing at some point with respect to time. Let's go back to the problem. The second that you've defined some variables, their derivatives are going to show up within the problem too. That is, you're going to have to know dx dt, or you'll have to solve for it. Same thing for dy dt. Like, you should either know these or have to solve for them. Well, here's a rate. It says the bottom of the ladder, this thing, slides away from the wall, which will increase this distance. It's going to get larger. 4 feet per second is going to be dx dt. That's how fast this variable is, in this case, increasing. So over here, I'm going to put 4. Do we know dy dt? And the answer is no. It says, how fast is the top of the ladder sliding down the wall? Well, that's the thing that we're trying to solve for. That's how fast is this distance decreasing? So this I actually don't know, but it's the thing I'd like to try to solve for. Since this variable is decreasing in size, I'm expecting this to be a negative number. So knowing this, can I figure out this? I'm going to take this equation and differentiate both sides with respect to time. I'll do that down here. We have x squared plus y squared is equal to 100. If I take the derivative with respect to time on both the left and the right, for x squared, I get 2x, and by the chain rule, I get dx dt. To that, I add the derivative of y squared, which is 2y. Also by the chain rule, you get dy dt. And on the other side, you take the derivative of 100, which is a constant, and that's equal to 0. I'm seeing that I can divide both sides by 2, so I get x dx dt plus y dy dt is 0. The thing I'm trying to solve for is dy dt, so I'm going to take this equation and solve for this. I'll subtract this to the other side and divide both sides by y. In doing so, my equation is dy dt, the very thing I'd like to figure out, is equal to negative x dx dt, all divided by y. Again, I took this and I subtracted it to the other side. To remove this y, I divided it to the other side of the equation. My goal is to figure out this, and hopefully I can figure out all the stuff over here to substitute into this equation. And the good news is, I know dx dt. It's positive 4. You could actually just put a 4 here. But I don't know x or y. I'll go back to the question and ask, is there anything that I'm missing here? And I see there's a 6. It says, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet away from the wall? This distance is x, and so they're asking specifically when x is equal to 6. I still need to know y, which is this distance here. Well, if you know x, and you know this is 10, and this equation connects x and y, you can actually solve for what y is equal to when x is equal to 6. Let's do that. That's 6 squared plus y squared is equal to 100. That is, y squared is equal to 100 minus 6 squared. Let's see, that's 100 minus 36. That's 64. If you take the square root of both sides, the square root of 64 is Well, it's technically plus or minus 8. I'm only going to take the positive solution because that's the only one that makes sense. We have it. If you want dy dt, it's equal to negative. X is equal to 6. Dx dt was given, that's equal to 4. And this whole thing is divided by 8. All right, so that's negative 24 over 8, which is negative 3. And that's negative 3 feet per second. The negative means your variable is decreasing in size, and feet per second because, well, if its distance is changing, this would have to be the corresponding rate. One thing to be careful about is how fast is the top of the ladder sliding down the wall? The way the question is phrased, sliding down the wall is indicating the negative. So in terms of your answer, you would only have to say positive 3 feet per second. So I'm going to put that up here as the answer. The answer is 3 feet per second. The reason that I did not include the negative is the way the question was phrased. Since it's saying how fast is it sliding down the wall, the down is indicating the direction, which is the negative. So I'll just include the unit as well as the absolute value of the number, which is 3. In example 3, we're told car A is traveling west at 50 miles per hour, and car B is traveling north at 60 miles per hour, and the cars are headed towards the same intersection. So if I'm going to draw a picture of this, here's the intersection. Car A is moving towards the west, and car B is traveling north, and they're going towards the same spot. So here's, we got car A, and here we have car B. Okay, one's going this way, the other's going this way. And we want to know at what rate are the cars approaching each other when car A is 0.3 miles from the intersection and car B is 0.4 miles from the intersection. This phrasing is interesting. At what rate are the cars approaching each other? I interpret this as the distance between the two cars, which I'm going to draw with a line like this. So this question is asking, how fast is this distance between the two cars changing as this car moves this way and this car moves this way? So here I have a picture that describes what's happening in this scenario. The next step is going to be define some variables and then set up an equation that connects these variables. I think an obvious choice would be something like, I see a right triangle, I'll call this side X, I'll call this side Y, and we're not actually told what this side is equal to, so I'm going to call it Z. What is the equation that connects these together? It is x squared plus y squared is equal to z squared. Can we now connect any of the numbers that appear within the equation to the variables that we have defined over here? Like, for example, do we know x, y, and z are equal to? And do we also know the rates? Do we know dx dt, dy dt, and dz dt? Well, I think we know x and y. We want to know what's happening when car A is 0.3 miles from the intersection and car B is 0.4 miles from the intersection. So that's got to be x and y. So I'll put in 0.3 and 0.4. And if you need to know z, well, here's an equation that connects them. You can put 0.3 here, 0.4 there, and solve for z. Z is equal to the square root of 0.3 squared plus 0.4 squared. And I know that is equal to 0.5. Now, do we know dx dt, dy dt, and dz dt? Well, we're told car A is traveling west at 50 miles per hour. So if this is x, then 50 must be dx dt. But I have to be careful. It's actually negative 50. And why is it negative 50 and not positive 50? X is decreasing in size, so I'll associate this negative with it as well. Dy dt is going to be how this side is changing. The car is traveling at 60 miles an hour, so it's going to be negative 60. And do we know dz dt? We don't, and that's okay. This question is actually asking, well, how fast is this line changing? In this case, it'll be shrinking. So I don't know what the answer is, but I do know it should be some negative number, and whatever that number is will be the answer to the problem. Okay, so from here, we have the complete setup. We have variables defined. We know what the variables should be equal to, as well as their corresponding rates and what we're solving for. I'm going to take this equation and differentiate both sides with respect to time. So we have x squared plus y squared is equal to z squared. On the left, we get 2x dx dt plus 2y dy dt is equal to 2z dz dt. I can divide both sides by 2, which will cancel those. And if I actually divide z to the other side of my equation, I'll have solved for dz dt, which is exactly what we're looking for. dz dt is equal to, I've canceled the 2's, so I have this stuff without the 2's. That is x dx dt plus y dy dt. It's all divided by z. I'll now simply plug in all of the given information. So let's see. X is equal to 0.3. dx dt is negative 50. Y is equal to 0.4. And dy dt is equal to negative 60. And this whole thing is divided by z, which is 0.5. And so I'm going to type this into a calculator and see the number that I get. Okay, I got negative 78. So the units on this are going to be miles per hour. So at what rate are the cars approaching each other? That rate, the answer to this problem is going to be 78 miles per hour. The reason I'm not including the negative here is down here, the negative is telling me that this line z is decreasing in size. And the question is already telling us that's happening. They're saying they're approaching each other. Therefore, I'm just going to say 78 miles per hour. If you included the negative, it'd be odd. You'd be saying, well, they're actually moving away from each other. It's like a negative, negative, becoming a positive. And for that reason, I'll leave the answer as just 78 miles per hour. In example 4, we're told person A walks due east on a path at 4 feet per second. 20 feet south from the path, a spotlight begins to follow him the moment he passes directly north. At what rate is the light rotating when the person is 15 feet from when the spotlight started following him? And we'll express our answer in rotations per second. Okay, well, for my picture, here's the person, and then down here is going to be the spotlight. And we're told, well, this distance is 20 feet. And that never changes. But the person is moving in this direction here at a rate of 4 feet per second. So the spotlight first shines on this person when they're here, and it follows them as they go in this direction. And so I'll, identify that with this line here. So here is my picture. Okay, I need to introduce some variables and hopefully set up an equation. And again, I see a right triangle in here, and it does make me think the Pythagorean theorem. But the information we're told is a little bit different. We want to know how fast the spotlight is rotating when the person's 15 feet away from here. And for that reason, I think what we actually want to label as one of our variables is theta. And the other thing that we know is, well, this side is increasing in length, so I'm going to call this side x. Now, you could label this side as a variable, like maybe y or z or something like that. But actually, you can solve for this side by using the Pythagorean theorem. If you square this side and you square this side, add them together and take the square root. That's the length of the hypotenuse. So we don't need a new variable. If you want to label this hypotenuse, this side, that's going to be x squared plus 20 squared, which is 400, and it's the square root of that thing. So now that we have actually defined a few variables, let's see if we can relate them back to any of the numbers that appear within the question. So to start with, we're told the person is walking at a rate of 4 feet per second. So that's not x, that's actually dx dt. It's equal to 4 feet per second. Do we know x? Well, we want to know something about the spotlight, the moment when the person is 15 feet away. So I think we want x to equal 15 feet. And we want to know the rate at which this light is rotating. So that's not theta. In fact, that's d theta dt. So this is the thing that we don't know, but we'd like to solve for. Is there an equation that will somehow connect thetas and x's together? And there is. In a right triangle, we can use some trigonometry. I think the one we want to use is tangent. Tangent is opposite over adjacent, so therefore tangent of theta is equal to x over 20. We can take the derivative of both sides of this equation. I think I'll rewrite it and multiply the 20 to the other side, but we have x is equal to 20 times tangent of theta. We know dx dt, that's the derivative of this. If you want to know d theta dt, you'll get that by taking the derivative of this side. Let's differentiate with respect to t on both sides of this equation. Dx dt is equal to 20. The derivative of tangent is secant squared of our angle. Maybe just for emphasis, I'll put that in parentheses. And by the chain rule, I have to multiply by the derivative of the inside, which is theta, with respect to time. This is great. I have an equation that connects dx dt to d theta dt. I know this, and I'd like to solve for this. I think what I'll do is divide both sides by 20 secant squared theta to get this by itself. So I'll write this as d theta dt is equal to, I'll put this as 1 over 20 secant squared theta dx dt. And, secant is the reciprocal of cosine. That's the same thing as just having a cosine squared in the numerator. I'll put it over here like this. D theta dt is equal to, this is really cosine squared theta over 20 times dx dt. So I know this, I just don't know what theta is equal to. But actually, it turns out you can figure out what cosine of theta is equal to. Here's what I mean. What is cosine of theta? If this is theta, cosine is adjacent over hypotenuse. So that's equal to 20, the adjacent side, over the square root of x squared plus 400. If you square this thing, that's cosine squared of theta. That's 20 squared, and if you square the denominator, it'll cancel the square root. And this gives us d theta dt is equal to, all right, so we get 20 squared in the top. There's still a 20 in the denominator, which I'm going to copy down. And then in the denominator, we're also squaring the square root of x squared plus 400. So that's x squared plus 400, just without the square roots. And then dx dt, we're told, is equal to 4. And, okay, great. Over here, I can take this 20 and cancel it with 1 in the numerator. So I get d theta dt is equal to, so that's 20 divided by, I have to know x, but we're told x is 15, so I'll put 15 squared here. This is 15 squared plus 400, and this is multiplied by 4. All right, so d theta dt is, all right, I'm going to do this in my calculator, but we have, let's see, 15 squared plus 400, that's 625. Then we have 4 times 20, which is 80. And 80 divided by 625 is, if we write that in a simplified fraction, that's 16 over 125. Now, what are the units on this? When you use trig functions, this is radians per second. So I'll put radians per second. It says to express the answer in rotations per second and not radians per second. How do you convert from radians to rotations. Well, if you do one full rotation around a circle, you've gone 2 pi radians. So I'll put rotation is equal to 2 pi radians. So these radians cancel. We'll have 16 divided by 125 times 2 pi. I'm running out of space. I'll put that exact answer over here. This is going to be 2 goes into 16 8 times. And we're still left with 125 and pi in the denominator. And this is in rotations per second. And that is the final answer. Before moving on to the next example, I'd like to do a quick review of similar triangles. In this right triangle down here, let's assume that the length of this side here is equal to 4. So the distance from here to here is 4. And let's say the length of this side is equal to 2. If I draw a triangle inside this triangle, like let's say like this, so they share this common angle here. If this side is length 3, going from here to here, can we figure out the length of this side? And the answer is yes, we can. The ratio of this side to this side is equal to the ratio of this side to this side, and you can set this up as a fraction. So the way I think I'll do it is I'll say 4 is to 3, so I'll put that as 4 over 3. That is equal to 2 over whatever this side's equal to. And I think I'll label this side here that we don't know, I'll call x. So it's equal to 2 over x. That is the ratio of this side to this side is equal to the ratio of this side to this side. Now we can solve this equation for x by cross multiplying. I'll put the x over here and the 3 over here, and we have 4x is equal to 3 times 2, which is 6. And if you want to solve for x, you can divide both sides by 4. And we get the x is 6 over 4, or 3 over 2, or really 1.5. Example 5 says, a water tank in the shape of an inverted circular cone has a height of 4 meters and a base radius of 2 meters. We are told that water is being pumped into this tank at a rate of 2 cubic meters per minute. And assuming that, how fast is the water level rising when the water level reaches 3 meters deep? There's a lot happening in this problem, but I'll start by drawing a picture. And that is going to be the picture of this inverted circular cone, which is the shape. Okay, it says that this cone has a height of 4 meters. So the height's going to be this distance here. So from here to here, we're told this is 4 meters. And we're also told that the base radius is 2 meters. And they're talking about this circle and the radius of it. So from here to, let's say, here, that radius is 2. All right. Okay, next. Water is being poured into the tank, and therefore the water level rises over time. And we want to know how fast it's rising once it reaches 3 meters deep, which we'll say is about here. I think one thing that'll help us to answer this question is if we draw the water level in at any height, which is right about here. That is, okay, if this distance is h for the height, and this distance here is r for the radius, can we figure out a formula for the volume of this cone? And the formula for the volume of a cylindrical cone of any height is 1/3 pi r squared h. So that is, you take the area of this circle, you multiply it by the height that it is, and you take 1/3 of that value. Now we've defined some variables in this equation. Let's see if we can relate it to some of the other numbers that appear in the question. So I already have used the 4 meters and the 2 meters for the entire tank itself. But it also says that we have water being pumped into the tank at a rate of 2 cubic meters per minute. So what is that? That's a rate, and that is a derivative. Well, I think that's going to be dV dt. So dV dt is equal to 2 cubic meters per minute. Because if that's how fast the water is being poured into the tank, that's how fast the volume of water is increasing over time. And the thing that we're trying to solve for is, well, how fast is the height of this amount of water increasing? That's referring to the variable h. So we want to solve for dH dt. So we're given this, but we're not given this, and this is the thing that we have to solve for. And we can do that by taking the derivative of this equation. However, there is an issue. To take the derivative of this equation, there's an h in it, which is good because we can get this derivative, but there's also an r, and we're not told anything about dr dt. What I'd like to do is a trick to remove the r from this equation so we're left with just h's. And how are we going to do that? Well, we're actually going to use similar triangles. So where are there similar triangles in this problem? If you look at this larger triangle here, I'm going to draw that below. So here we have this larger triangle. I know it has a 4 and a 2 for the length of this side and this side. Now, on this inner triangle here, which I'll draw like this is H and R. And these are similar triangles. This triangle is similar to this one. And what that means is 4 is to H as 2 is to R. And I can set that up in a fraction like this. 4 over H is equal to 2 over R. This is an equation that connects H's and R's, meaning you can solve this for either H or R. Then you can take that information and put it into this formula, eliminating one of the variables. I'm going to cross multiply. I'll put the R on this side and the H on this side. So we get 4R is equal to 2H. And I'm going to divide both sides by 4, which gives us R is equal to H over 2. The reason for this is, if we have R, we can put it here to get rid of the R and have just H's in this equation. Let's do that. Volume is equal to 1/3 pi. R is really H over 2. We're squaring that, and that's H. If we simplify this equation, volume is 1/3 pi. H squared is H squared over 2 squared, which is 4, times H. We can combine this and say, well, we have 1/3 and this 4 here that gives us a 1/12. We have pi, and we have H squared times H, which is H cubed. This equation in this setup is equivalent to this one. What's nice about this is we can take the derivative with respect to t, and there are no r's that we have to worry about anymore. So let's do that as our next step. Let's differentiate this with respect to t. We get dv dt is equal to, okay, if I bring down the 3, I get 1/4. I get pi h squared times dh dt. I know dv dt, that's 2. I know h, we're told that's 3. And the only thing I don't know is dh dt, which is the thing I'd like to solve for. If we plug all this in, we get 2 is equal to 1/4 pi. H is 3, because we're told we want to know this rate when the water level reaches 3 meters. So that's 3 squared times dh dt. Okay, this means I'm going to multiply 4 to this side, divide pi, and divide 9. So we have 8 over 9 pi is equal to dh dt. So 8 over 9 pi meters per minute is how fast the water level is rising once the water level reaches 3 meters deep. In example 6, we're told that the minute hand on a watch is 8 millimeters long, and the hour hand is 4 millimeters long. Using this information, can we determine how fast the distance between the tips of these two hands is changing at 1 p.m.? What I did is I drew a picture of the watch, and I labeled the minute and hour hand with 8 and 4 millimeters respectively. And the thing that we're trying to solve for is the rate at which this distance is changing at 1 p.m. What I noticed is this figure actually defines this triangle. It's not a right triangle, so we can't use the Pythagorean theorem, but I do know of this other formula that's very similar to the Pythagorean theorem, and it's called the law of cosines. If you know side A and side B and the angle between them, then the length of this side here is determined by this formula. So again, after I drew my picture and I noticed that there was this triangle, I figured out that this formula will help me solve for the rate at which this is changing. So what we're trying to find is, I want to find dx dt, and that happens to be at 1 p.m. There's also this other variable in the problem, which is theta. So I'll need to know what d theta dt is equal to. So I want to find this. And to do so, if I'm using this formula, I'll have to know what this thing is equal to. So let's put all of this information into this formula, and let's see what we get. So for starters, c, I'm actually relabeling it as x, so I'll just call x squared. Okay, a in this case is equal to 8, and if you square it, you get 64. And b squared, which is this side, is 16, minus 2 times a times b. A times b is 32, and if you double it, you get 64. And then we have cosine of theta. And if we simplify this, that is x squared is equal to 64 plus 18, which is 80, minus 64 cosine theta. To find this rate, I'll have to take the derivative of this equation. So let's do that. If I differentiate with respect to time, I get 2x times dx dt is equal to, the derivative of 80 is 0. The derivative of cosine goes to negative sign. The two negatives will cancel to make it positive, and the 64 will remain. It'll be positive 64 sine of theta, and by the chain rule, you have to multiply by d theta dt. So to know this rate, you have to know x, sine of theta, and d theta dt. I'll solve for this by dividing 2 and x to this side of the equation. I'll note that, well, 2 cancels to a 1, and it goes into here 32 times. dx dt is equal to 32 sine of theta all over x times d theta dt. All right, well, to start with, what is x? And that's going to be this length at 1 o'clock. And I can go back to this formula to figure that out. But that means I'll need to know what theta is equal to. So to get x, I have to know theta. And that is, what is this angle at 1 o'clock? So up here, this is 12, this is at 1, and so on. Well, it's divided into 6 equal parts. So if you do one full rotation, that's in radians, 2 pi around. And if you divide that into 12 equal pieces, that means you get pi over 6, which is this angle here, which is actually this angle here. So if we want to find x, x is equal to the square root of, going back to this formula here, we have 80 minus 64 cosine of pi over 6. And I'll have to get some decimal for this, so I'll get that from my calculator. Rounded to 3 decimal places, it's about 4.957, and that's in millimeters. Okay, great. I know x. I know theta. I can just put a pi over 6 here. The only thing that I don't know is, what is d theta dt? That's the rate at which this angle is changing. And at 1 p.m., It's definitely a negative rate. So how would I figure out that? I'll put my work for that over here. Again, our goal is to find d theta dt. That should be the rate that the hour hand is traveling around the circle minus the rate that the minute hand is traveling around the circle. So if we take the difference of those two rates, so I'll write that over here, the rate of the hour hand minus the rate of the minute hand. So the hour hand makes a full rotation. It goes 2 pi in 12 hours. So that's 2 pi over 12 minus the minute hand makes a full rotation 2 pi radians every hour. So 2 pi over 1. So 2 pi over 12 minus 2 pi over 1 is negative 11 pi over 6. This is the rate at which this angle is changing. It changes negative 11 pi over 6 radians every single hour. Let's take all this information and put it into this formula. Again, we know x, we know theta, and now we know d theta dt. So my final answer is that dx dt is equal to 32 times sine of pi over 6 divided by 4.957 times negative 11 pi over 6. I will plug this into my calculator to get a decimal approximation. Okay, I'll round it out to 2 decimal places, but the rate is changing at 18.59. The distance we're talking about is millimeters. And since I expressed this rate in terms of hours, that's going to be millimeters each hour. So that is the rate at which the distance between the tips of these two hands is changing the moment that it arrives at 1 p.m. Example 7 says, in a square room with sides 20 feet long, a brother and sister rat are both eating cheese. The brother on the east side directly opposite the sister on the west. And then all of a sudden, an exterminator enters the room. The brother runs north at a rate of 4 feet per second, and the sister runs south at a rate of 6 feet per second. All right, I'm going to draw a diagram describing what's happening in this scenario. So here's the brother, here's the sister. They're directly opposite each other at the starting point, a distance of 20 feet. And then here, the brother's running north at 4 feet per second, and here south at 6 feet per second. And we want to know the rate at which the distance is changing between these two related rats. So that distance is going to be this line here. So we're looking to figure out the rate at which this line is actually increasing over time. All right, to solve this problem, I'm going to start labeling some variables in here. I'll call this side x and this side y. This means that dx dt is the rate at which the brother is running, which is 4 feet per second, and dy dt is the rate at which the sister rat is running, which is 6. I'm going to call the side we're looking at z, and our goal is to find dz dt. What is that equal to? And it turns out there is a triangle in this problem. Here's one side is z, this side is 20, and this side is x plus y. So what's the formula? The formula is, well, this side is 20, so it's going to be 20 squared, plus this whole side is y plus x. I'll say x plus y squared, and that's equal to z squared. And I'll write the 20 squared as 400. What else do I know? If we're looking for this, I want to take the derivative of this equation. We're also going to have to know what x and y and z are equal to. We'll have to put those numbers into the formula as well. We want to know what's happening in this scenario after 1 second. Okay, so we need to know, well, what is x and what is y? Well, x, the rate is 4 feet per second, so after 1 second, the distance of x should be 4. Likewise, this rate is 6 feet per second, so after 1 second, that distance is 6. And if you want to solve for what z is equal to, I can put x and y into this formula and solve for z. So I'll express that as z is equal to the square root of 400 plus 4 plus 6 squared. And I'm just going to get that number in my calculator. Okay, the exact value is the square root of 500, and rounded to, let's say, 2 decimal places, that's 22.36, and that would be feet. Okay. We can now take the derivative of this equation to solve for dz dt. If you take the derivative of 400, it's 0. Starting here, when we take the derivative, we get 2 times x plus y to the first. By the chain rule, we have to multiply by the derivative of the inside, which is dx dt plus dy dt. On the other side of my equation, I get 2z dz dt. Here, I can cancel 2 from both sides of my equation. In fact, I can solve for dz dt by dividing z to this side of my equation. We get that. I'll put dz dt is equal to this whole thing divided by z, because I already canceled the 2's. So we get x plus y times dx dt plus dy dt all over z. And I know all of those things. I'm just going to plug these numbers in and see what we get. Okay, so x is 4, y is 6, dx dt is also 4, and then dy dt is also 6. And z, the exact value, I'll put in the exact value, it's the square root of 500. So let's see, the top is 10 times 10, which is 100 over the square root of 500. If we want an approximation for this, that's 100 divided by the square root of 500. And that's rounded to 2 decimal places. It's a positive number. It is 4.47, and I know it's a rate with feet per second. So that is the rate at which this distance is changing at this moment.